Text-to-image generation is where you go to an AI system, let's say inside an online service, and you say, generate me an image of so-and-so. So it could be, generate me an image of a guinea pig on the moon sipping champagne, or generate me an image of Marie Curie and Einstein having dinner. Then the service serves up images which often look like what you wanted, even if you've asked for quite outlandish things. I'm sure most of you will remember when this seemed like science fiction, as that's only a few years ago. At the heart of these services are diffusion models, which, like transformers, which we cover in the next part of the lecture, are a jewel in the crown of generative deep learning. To understand where diffusion models come from, we have to go back briefly to GANs, generative adversarial networks. As mentioned previously, GANs were being used for all sorts of artistic applications, and AI artists were becoming relatively famous. There was one final invention which really supercharged GANs even more by enabling people to prompt them with text and get an image produced which looked like what was described in the text. During the GAN era, OpenAI, a very influential company specializing in deep learning, they dropped a model called CLIP without much fanfare. They made the model open source, which meant that lots of researchers, including me, were able to download it and play around with it to their heart's content. For me and others, CLIP changed everything. So CLIP stands for Contrastive Language Image Pre-training. So it's a trained neural model that embeds both images and text into the same latent space. Recall that an embedding of an artifact is a representation of it as a tensor of floats in latent space. The embedding is somehow meant to capture the most important essence of the artifact and act as a good substitute for it. Now, the cool thing about CLIP is that both images and text can be mapped into the same latent space. So if an image and a piece of text show and describe the same thing respectively, then they will be close to each other in the latent space. So an image of Superman and the word Superman will be embedded from their artifact space into the latent space, and they'll be close together in that space. An image of a guinea pig and the word Superman are going to be mapped to very different parts of the latent space, so not close to each other. CLIP was trained as two models, one to embed images and one to embed pieces of text. The data used was pairs of images and captions of them, scraped from the internet, where captioned images are plentiful. In fact, OpenAI scraped 400 million such pairs. Now, a caption for an image describes what's in it, but we could also say that the image reflects what the caption says. During training of CLIP, good pairs of an image and its actual caption were used, but also bad pairs of an image and a completely wrong caption were used. For backpropagation, output from the loss function was reduced if the distance between the latent spaces for embeddings of a good pair was small. The loss function was also reduced if the distance in the latent space for the embeddings of a bad pair was large. So we want good pairs to be embedded in the same spot and bad pairs to be embedded in spots which are quite far away. That's why it's called contrastive learning. You're comparing and contrasting your pairs. Using the same loss function for both embedding models, training essentially forced the models to map similar things, whether text or images, to the same place in the latent space. Then we could use a standard distance, such as a cosine distance, to tell how closely a piece of text captions an image, or how closely an image reflects what the text is saying. While there had been limited success in text-to-image generation using conditional GANs, the earliest really good approaches to text-to-image generation were CLIP-guided GAN generators. An important one of these, called the Big Sleep, was using Big GAN as its generator. So, given a text prompt like the word Superman, the Big Sleep worked by starting with a random latent vector and then generating an image with Big GAN. CLIP was then used to determine how close the image was to portraying what the prompt said, but more than that, the distance between the prompt and the image was information that could be used to determine a gradient. So just like with backpropagation. The gradient defined the direction in which the random latent vector should go in order for Big GAN to reflect the text prompt a bit better. So then you move it you generate an image from the moved latent vector, work out how far that is from what you want in terms of reflecting the text, and get a new direction, move it again, move it again, move it again. And after 30 or 40 moves like this, the image starts to look like the text describes. And after 100 steps, the image really looks like what the text describes, albeit quite abstracted a lot of the time. The results from this were eye-opening and groundbreaking, and set up a race to produce better, faster, and more impressive text-to-image generators. I did the first proper scientific experimentation with the Big Sleep, and it really was amazing. But, as usual with deep learning, the approach has been superseded, and the best we have at the moment are diffusion models for text-to-image generation. So diffusion models were being worked on in a separate line of research, which didn't seem particularly promising at first. They produce images in a very different way to the generators of GANs or autoencoders. And their approach with diffusion models is based on noised images. So to noise or diffuse an image, you take the red, green and blue values of the pixels and you move them around randomly. If you only move them a small distance, then the noised image will still look mostly like the original with a bit of noise. But the more and more you move the pixel values, the more noisy the image gets, until there's really no sign of the content from the original image. Now, diffusion models start with an image which is completely noise, albeit a special type of noise called Gaussian noise. And in multiple stages, they're able to turn that noise image into a realistic looking image. And it does through a series of steps called denoising. So how do they work? How do diffusion models work? Well, it helps by first thinking about how they're trained. So imagine you have an image that you want to train a diffusion model to construct entirely from noise. You could add, say, 10% of noise to the image by moving the red, green and blue values by each pixel by up to 10% away from their starting positions. So the image would still look like the original but would be a bit noisy. You could then train a neural model to be able to reverse this process so that it denoises images which are only 10% away from real images. The loss function for this will be based on how close the denoised image is to the original, which was noised in the first place. Suppose then you take the 10% noised image and you add another 10% of noise. You could then train a neural model to reverse that process, so taking a 20% noised image and turning it back into a 10% noised image. This could go on until you've got a 100% noised image. So if you train 10 separate neural models to incrementally denoise images 10% at a time, this means that you can essentially start from a random noise image and produce a realistic image from it after 10 denoising steps. This is basically what diffusion models do. The individual denoising models are a special type of neural model called a U-net, which I won't go into details of, but they start with the data from an image. They reduce it down to a smaller latent space and then they expand it back up, a bit like an autoencoder. And when you draw a diagram of that, you can do it in a U-shaped way, so that's where they get their name from. So as we've currently described it, the diffusion model wouldn't be all that good for two reasons. Firstly, this approach is unfortunately very slow. And this is why it didn't look promising to start with. That's because there are 10 or more stages, and each pixel in the image has to be denoised individually at every stage. So there's no real scope to reduce dimensionality to make it faster, or to parallelize it further to make it faster. And the second reason it wouldn't be very good is it's not yet driven by a text prompt. So to address the first problem, researchers in Germany came up with the genius idea of moving the diffusion process from the outer space of images into the latent space. So there they called it latent diffusion. So if we remember that we can encode an image into a latent space so that the encoded version of it can act as a smaller substitute, but it's still possible to regenerate the accurate version of the output of the original through the decoding process. So that means that we can encode an image, we can noise the encoding of it, we can then denoise that latent space version of it, and then we can decode the denoised vector. So it's quite a long, complicated process, but it works. And because the latent version of an image is substantially much smaller than the actual image, the process is much faster. In fact, the move to the latent space really saved diffusion as a viable approach, otherwise it would have just been too slow. To address the second problem, we can introduce conditioning. The training set for image diffusion models is, like it was for CLIP, pairs of an image and a caption which describes the image. So when each denoising model is trained to turn a noisy image into a less noisy one, a representation of the caption for the image is added to the input, just like the one-hot vector was added to the input when Big GAN was trained to do conditional generation. In fact, a good choice for the representation of the caption is to use the embedding of text that you get from the CLIP model that we previously discussed. The one advantage of that is that images can be also embedded by CLIP. So instead of asking to denoise an image to match a text caption, you can ask to denoise an image to match another image, because that can be encoded via CLIP into the same latent space as you would text. So you can really ask these systems to generate images which look like your given image. And that kind of multimodality, working with text and images, has really driven forward the value and ease of use of generative AI models. There was a big moment in the world of generative AI when a London-based company called Stability AI dropped a model called Stable Diffusion. It was a diffusion model. Other companies like Midjourney and OpenAI, they developed brilliant image generation models, but they were very much closed. They were kept to themselves, and they only allowed people access through carefully controlled portals. In contrast, Stable Diffusion was dropped open source, with a technical paper describing how it worked and code to get it to work in your own application. And as a result, there were thousands of people, including me, who investigated it and improved upon it, found new uses for it, and then eventually built companies and apps around it, and generally drove forward AI research and development into diffusion models and generative AI in general in a massive way.